we modeled Rutherford scattering experiment in Python. And trust me, the results are surprisingly real. You are about to see what actually happens inside the nucleus, particle by particle. So basically, this starts with a basic simulation, and the best results comes from Monte Carlo methods, where physics meets randomness and it still predicts the truth. We will talk about it in my next video. Before we dive into the code, let's quickly understand the physics behind it. Once you get the concept, the simulation will blow your mind. So let's get into it. Rutherford's nuclear model of atom 1911 is an outcome of the scattering experiments of alpha particle conducted by his colleagues Geiger and Marsden. So fast alpha particle, which is helium ions, basically He plus 2, are emitted spontaneously from PO214 and hit the gold foil, which is only a few thick. As alpha particles hit the foil, some pass through and some bounce back, or bounce in different direction, you can say. So based on the scattering experiment, Rutherford proposed that the atom consists of a tiny but massive positively charged region called the nucleus, and the cloud negatively charged electron surrounds the nucleus at a distance. So practically the nuclear radius, I think it's around 10 to the power minus 14 meter, and for an atom it is 10 to the power minus 10 meter. So in that whole experiment, there are few points you have to understand. First thing, the alpha particles which are positively charged were produced from a radioactive source, which is PO214, and these particles were sent in a narrow beam through a small hole in a lead screen. Okay, so the beam then hit the gold foil, which is only few thick, and a special screen coated with a zinc sulfide was placed around the foil. Why? Because when an alpha particle hits this screen, they produce tiny flashes of light, which is called scintillations, and a microscope was used to observe and count these flashes. So this setup helped them at that time understand how the particles were scattered after hitting the gold foil. So as a result, most of the alpha particles went straight through the foil, meaning most of the atom is empty. A small number of a small number of alpha particles bounce at big angles, even nearly 180 degrees. So this was surprising. So according to their older Thomson model, such large deflection should not be happen. Okay, the Rutherford explained that only if there is very small, very heavy and positively charged core, which is nucleus, so alpha particle be pushed back with such large forces. So he proposed the idea of the nucleus, and the electrons were thought to be outside of the nucleus. So this model became known as the new nuclear atom model at that time, to explain why atoms don't fall apart. So Rutherford said, see, electrons revolve around the nucleus just like planets go around the sun. So the main limitation of the model is this, that the model could not explain the stability of electron in the atom. Let's code this in Python. So to model this, I am using Glow script. So it's super easy and much fun to use. No need to use any fancy application. You can do it by one click from your computer. So visit glowscript.com. Here, first I have to define the gold atom. AU equal to sphere, POS equal to position vector is, let's say, 0, 0, 0. Okay, color equal to color dot yellow, charge equal to 79, I guess, and radius, let's say for visibility I'm giving 0.1. Then next one is alpha, or helium ions, alpha particle. So in alpha particle sphere, which have a position vector POS equal to vector, it is coming from negative x, so let's say -1, and I'm giving some shift along the y-axis, that is 0.1, let's say, and z equal to 0. Velocity equal to vector 0.100. Okay, charge equal to 2 and mass equal to 4, as helium plus 2, 4. Okay, radius equal to, let's say, 0.01, color dot red, and I want to see the path, so make trail equal to true. That's it. Okay, so now I have when alpha particle comes near to the nucleus, it will experience some Coulombic force. In Coulombic force, k q1 q2 by r square. So I have to define k equal to, let's say, for just calculation purpose, I'm giving 2 10 to the power minus 5 or 2e minus 5, and then dt, the variable is 0.1, and then I'm using for loop for to model this. So for t in range, the initial value is 0.1, final value, let's say 16, okay, and step size is 0.1. Then I have to animate this, that's why I'm giving rate equal to 50. So I'm telling Python, please do not calculate more than 50 times in 1 second. Now I have to define force equal to k into alpha dot charge into au dot charge. That means q1 into q2, into k q1 q2, okay, by a magnitude of alpha dot cos r square, okay, and the force is acting along the direction of r, so head of, sorry, into at alpha dot cos k q1 q2 r square into r cap. That's it. So now I have to update the velocity. That means alpha dot velocity equal to equal plus equal to equal to force by mass. It is acceleration. So force divided by alpha dot mass into spelling mistake, into dt. Okay, now I have to update the position. Alpha dot cos equal to alpha dot velocity into dt dot velocity into dt. So first I calculated that force, then update the velocity equal to v plus force by mass into dt, okay, and then I have to update the position equal to position plus alpha dot velocity vt. Nice, okay. So that's it. For our modeling purpose, I am using another one loop. If magnitude of alpha dot cos greater than is qrt square root of 3, then alpha dot velocity equal to vector 0 0 0. That's it. Okay, so let's run it. So before that I have to save and give a name, Rutherford experiment. Okay, experiment. Okay, save it and run it. So you can see this red one is our alpha particle and the yellow one is our gold atom or gold nucleus. So when alpha particle approaches to the new nucleus, it experiences Coulombic repulsion force and it diverts from its path. Okay, so you can also plot the position, the alpha particle position with respect to time. So from that plot you can have an idea the impact parameter, the closest approach or the closest path or closest distance in between the alpha particle and the gold nucleus. So let's plot it. Okay, for plotting we need first curve f1 equal to g curve, let's say color equal to color dot green dot equal to true. Here I have to give a command. Oh, sorry. I need one graph paper also, no? So that's a g1 equal to graph graph which have x title equal to let's say time, and y title equal to let's say position. Okay, and give some height equal to let's say 500 and give some width, let's say 500. So here I already gave a graph and a curve. Now I just write down one command that f1 please plot in that graph along the x-axis is t and along the y-axis is alpha dot position. But here is the trick. Here T is the scalar quantity and alpha dot pos is the vector quantity. So that's why we have to use magnitude of alpha dot pos. That means it converts this vector quantity to scalar quantity, or we just need the magnitude. That's it. Now if we run it, then see. So from here you can see, or you can understand this closest distance in between the nucleus and the alpha particle is here. Okay. Okay, so in such a way you can plot, or you can analyze the velocity with respect to time and force with respect to time. Let's do it. I want to signature, so let's copy paste it. Control C, Control V, another graph, another curve for F2, color let's say blue. Okay, then I have to give again one command, that is please F2 plot a graph between F2 T and let's say velocity. So magnitude of alpha dot velocity. That's it I think. Let's run it. Yes. Okay, to understand this, or for better understanding, I just mute this position curve once, and mute. Let's see. Mistake, silly mistake. Let's run it. See, here is the velocity nature. So now I want to plot the force with respect to time, and we will plot this displacement, velocity and force in a same graph. So here is the trick. You have to put another F3, and let's say it's red color for force, and just copy it and paste it. F3 dot plot T, comma force. Force is also a vector quantity, so magnitude of force. Okay, let's run it. See, so in the same graph we plotted the position, velocity and the force, and you can see, or you can understand. Let's see, just a minute. If and if I mute the positional ones, if one, then you can see the blue one is our velocity, okay, and the red one is our force, and the force is coming from m dv. So it's basically the nature of the force curve. It's just like derivative of the velocity curve. So you can understand from the mathematical point of view also. So that's it. So if you want to plot all these three curves in one graph paper, then you run it again, and it plotted in the same graph the all displacement, force and position. So in our physics modeling, there is some limitation that only one alpha particle is coming instead of a shower of an alpha particle. It's a very simple model, and here we didn't assume that Bremsstrahlung part and all other complex scattering parameters. You can put all that complex parameters into this and analyze all that. In my next video, I am going to do it with Monte Carlo simulation, or this is the same Rutherford experiment. You can see from Monte Carlo simulation, you can create a shower of alpha particles.